Subhadip sir, can you hear me, Subhadip sir? कुछ आपका
Am I audible now?
Yes, sir, you are audible.
Okay. So good morning once again. I welcome you all to this Northeast Center for Technology Application and Reach, Nectar sponsored one-week online entrepreneurship development program on flexible 3D printing operation and prototype development, organized by the National Institute of Technology, Arunachal Pradesh, in association with Procaushal, the Startup Cell and Innovation Center, NIT, Arunachal Pradesh, India. We are really privileged to have amongst us our director, sir, Professor Pinakesha Mohanta, sir, and we have also been joined by our today's expert, Dr. M. Durai Silvan, sir, professor from the Department of Production Engineering, National Institute of Technology, Tiruchirappalli. Before starting off the session, I would like to request our program coordinator, Professor Dr. Prasesh Kumar Mohanty, sir, to kindly brief us about the Entrepreneurship Development Program. Sir, please.
Okay, thank you, sir. Respected director, sir, our today program expert for flexible 3D printing operation and prototype development, Professor Durai Silvan, sir, from NIT Tiruchirappalli, faculty members of NIT Arunachal Pradesh, program coordinator, and all the participants. Very warm greetings and one good morning to one and all present through this online mode. Once again, on behalf of National Institute of Technology, I am pleased to welcome you all to this one-week entrepreneurship development program on flexible 3D printing operations and prototype development. So organized by NIT Arunachal Pradesh and sponsored by Northeast Center for Technology Applications and Reach, DST Government of India. So first of all, I would like to express my gratitude to our director, sir, for his generous support and always inspiring us to organize such type of entrepreneurship development program and kind presence here today. Thank you, sir. I also thankful to Professor Durai Silvan, sir, given his positive consent to deliver the talk on this introduction to additive manufacturing and also agreed to show the live demonstration of 3D printing despite of his busy schedule. So not wasting much more time, I just like to give a brief about this training program. So the topic of this training program is flexible 3D printing operations and prototype development. So as you know, 3D printing technology has been evolved as an interim field of science and has witnessed an enormous market potential in establishing a replacement of module within the field of construction, designing, automobile engineering, architecture, and many more. And this 3D printing is also known as this additive manufacturing when it has been turned digital 3D printing models into solid objects by building them up in the form of layers. The technology was first invented within 80s, and since that point, it has been called as rapid prototyping. However, within this previous couple of years, 3D printing has additionally begun to evolve next generation manufacturing technology that has the potential to permit local on-demand production of ultimate products and parts thereof. These technologies are employed when these are within the field of automotive industries, geographical information systems, footwear, industrial design, then dental and medical industries, engineering and construction, aerospace, jewelry, and many more. And this EDP will provide a suitable exposure for 3D printing technology and development of prototype 3D printing with live demonstration from various resource persons of NIT, IITs, and reputed organizations. And last, I hope this one-week FDP on this flexible manufacturing, flexible 3D printing operation and prototype development is to expose the participants to keep the steps in startup venturing process and equip them with the adequate knowledge to initiate a venture in 3D printing technology. Also, they equip them with the requisite skills, knowledge, competencies to convert their startup idea into a viable business entity. Thank you. What is that?
Thank you, sir. Now I would like to invite our director, sir, Professor Pinakesha Mohanta, sir, to kindly brief us the audience. Sir, please.
Yeah, good morning. Namaskar. Professor Durai Silvan from NIT Trichy, our organizers, Dr. Subhajit Das and Dr. Process Kumar Mahanti, their participants, students, and other guests. A very welcome to all of you to this particular 5-day entrepreneurship development program. This program is an initiation based on the funding received from the organization called Nectar under DSIR. And the theme of this conference is flexible 3D printing operation and prototype development. This 3D printing has whatever we call additive manufacturing or rapid prototyping, all have this almost same meaning, and it actually creates an avenue for going for entrepreneurship development. In conventional machining or conventional manufacturing technology, some of the intrinsic or precision things cannot be made, or high-end equipments, high-end products cannot be made, which is possible with the help of 3D printing. So this may open up a lot of startups, plus few of them can go for entrepreneurship development. That is the main aim of going for this kind of entrepreneurship development program. Now, NIT Arunachal Pradesh is constantly giving a lot of workshops, generating a lot of workshops from last 2 years under Nectar, or also faculty development program in various fields. Under this Nectar program, we are not only related to 3D printing or flexible manufacturing, rather we are starting from ground level like pickle making, then banana fiber extraction, then another thing is electrical wireman. So depending upon the level of the particular unemployed persons, we are generating different type of workshops. But this is a high workshop because where pre-hand knowledge of engineering is required, particularly mechanical engineering or manufacturing or production is required. I hope this program will be very much encouraging, and it will be knowledge sharing from all the resource persons who have been invited. So I could see more than 120 participants have already registered for this particular program. So I welcome you all to interact for this 5 days program. And later on, my request is when the COVID situation will improve, I think 2-3 days hands-on workshop can be held on the similar line at NITAP because we have the facilities here. Thank you. Thank you all of you.
Thank you, sir. Thank you for your encouraging words. Dr. Durai Silvan has joined, sir. So, are we listened to? Are you able to listen to us?
Yes, sir. I am able to listen. Am I audible?
Yes, sir. Yes, sir. Okay.
Yeah. Good morning, sir.
Yeah, good morning. We are very much pleased to have amongst us Dr. M. Durai Silvan, professor from the Department of Production Engineering, NIT Tiruchirappalli. Before starting off the session, I would just like to brief you all about the speakers for today. Sir is currently professor in the Department of Production Engineering, NIT Trichy. Sir has completed his PhD in 2006 from Technical University of Clausthal, Germany. Sir has also completed his MBA in Business Administration in Operation Management in 2001 from Madurai Kamaraj University, Madurai. And Sir has also completed his ME in 1998 from NIT Trichy. Sir has a total experience of 21 years since 1999 and has been actively involved in academics. Sir has also been awarded the German Academic Exchange Service Fellowship between June 2004 to September 2006 to do research at ISAF Technical University of Clausthal, Germany. Sir has, to his credit, a number of projects funded by different sponsoring agencies. To name a few, 3D modeling and engineering design validation of 12-meter e-bus sponsored by Bharat Heavy Electricals Limited, Government of India in the duration 2018-19, which is costing around 34.4 lakhs. Sir has also been actively working in the field of design of thermal performance evaluation systems with charging discharging circuit of lithium-ion batteries for e-vehicles. And Sir has also been the life member of the Institute of Engineers India, and Sir has been actively associated with reviewing of very international journals of repute such as Surfaces and Coating Technology, Material Science and Engineering Part A, Surface Engineering, Materials and Design, Journal of Advanced Manufacturing Technology. Sir has to his credit 58 number of international journals and 28 number of international conferences, to name a few. So with this very brief introduction, I would like to now invite our speaker for the first session, Professor M. Duraiselvan, sir, to kindly start off the proceedings. Sir, please.
Yeah, thank you, Dr. Subhajit Das, for a nice introduction. So I have a little connectivity issue. Hope I am audible. And so throughout the presentation, I request some of the moderator be with me if there is any kind of disturbance in terms of slide change or slides are not visible. Someone need to alert me, because in online the speaker perceive that it is audible to everyone, the slides are visible to everyone, but sometimes there may be little connectivity issue. And probably I request the organizer to also record the presentation if possible, because many might have logged in through their mobile phone. There may be some data streaming issues. At a later stage, they can view it leisurely. So with that few words, I will start my presentation. And yeah. So now I am in a presentation mode. I hope the slide is visible. So I first of all wanted to take Subhajit Joss for contact me through one of my friend to deliver a talk on this particular topic. And I thank NIT Arunachal Pradesh organization, specifically the director, the deans, and other faculty members of Mechanical Engineering Department for giving me an opportunity to present in this forum. And very recently, we have procured one 3D metal printer. And earlier to that also, close to a decade, we are involving in direct metal laser deposition. So as Dr. Swajit mentioned, that I did my PhD in Germany in 2006, and basically on laser cladding. And this direct metal laser deposition, again, more of cladding related. And there are different varieties by which we can realize the material deposition layer by layer. And when you talk about metal printing, laser becomes an inevitable source. And majority of the commercial printers do have a laser-based system. And very recently, we are witnessing electron beam-based deposition techniques that is flourishing due to several advantages. But still, the laser-based additive manufacturing, in many ways, that is highly commercialized. And I have organized this particular presentation. Mostly, I am not going to cover any particular topic in detail. Rather, I will give a more generalized idea about what is 3D printing or additive manufacturing. These two words sometimes interchangeably being used. And nowadays, the best way to call this kind of a layer by layer deposition is additive manufacturing. We are adding material layer by layer rather than calling it 3D printing or metal deposition technology, something like that. So I will give a very brief introduction. Then what are the different classification? Not only metal-based processes, but also we all quite involved in that fused deposition modeling based printers also. I try to cover the entire spectrum of classification of AEM processes and different applications of these processes. Then what are the facilities that is available at NIT Trichy and the key challenges, and why that additive manufacturing that is being relooked in the recent time, that even though it's been there in practice for more than 20-30 years, because of the fact we are talking about more on industry 4.0 or the smart manufacturing system, where we need to come out with any kind of variations and making it realizing in terms of prototype. And for that, definitely this additive manufacturing becomes part of the system, and thus it regains its position, and it becomes an inevitable source in Industry 4.0 application. So that also briefly I try to touch upon in this, the role of AEM in Industry 4.0. So basically, compared to other conventional manufacturing technology, this additive manufacturing is a young technology, and in 1984, it got introduced to the world in the form of stereolithography. And Charlie Hull, who is the first one to prove that some kind of a digital model that can be converted into a 3D prototype. And the stereolithography, it is a forefather of all the technology what we are talking about, the 3D printing from the physical objects to from the digital data to converting into a physical object. And when you look at this flow diagram, and first you need to create a 3D model, and that 3D model will get converted into STL file. And STL file, it's a kind of a file that is where the system will understand. And through the slicing software, this model is converted into layer by layer slicing. And through some kind of a AEM process, you can build those layers to form a 3D object. So when you look at in the flow cycle, from a CAD model to 3D object, you can directly convert. So by saying that, you don't need any kind of a complex tooling, complex dice in order to do that prototyping. Rather, if you simply create a model and irrespective of the complexity, you can convert into a form of a prototype, which in the present scenario, the highly competitive industries is requiring, as you need to come out with so many varieties in multiple verticals, the different products in order to cope with the changing scenario. And if you are spending years and years to convert the prototype into the market ready product, then you'll be losing the market with your competitor. And in that sense, this kind of quick prototyping, rapid prototyping is becoming an essential part of everyone's manufacturing strategy. And the 3D printing plays a vital role in realizing that kind of rapid prototyping. And when you look at that ASTM specification of what is 3D printing, it's a process of joining materials to make objects from 3D model data, usually layer upon layer, as opposed to subtractive manufacturing methodology. So generally, when you look at that, we have an ingot or casting. From that, we are machining out the parts, and finally we are realizing the kind of a product of ultimately. And the wastage of material in this case is very huge. But here in the case of 3D printing, we are not subtracting material, rather we are adding material. So when you say that, even this can be considered as a zero wastage process, except that some kind of a support material is required in order to support any kind of overhanging parts. In rest of the cases, it is self-supporting. And many wanted to realize this 3D printing as a form of substitute for mass production, which can never be done, because you know that you are depositing layer by layer, and the deposition layer thickness also running into a few tenths of micron, and definitely it cannot match the speed of or the productivity of the mass production systems. And when you wanted to produce something in a larger quantity, 3D printing may not be a suitable alternative compared to conventional or traditional technology. And where the 3D printing is really competing is when you have a very high complexity. Later, I will show some of the applications and other areas where the 3D printing that is finding quite interesting applications. And at no point of time, you cannot match the complexity that it can do with a conventional manufacturing system. So in that sense, for a low volume, complex or a unique products, 3D printing is more suitable. And when the volume is too high, and if you are looking at something from the cost perspective, and 3D printing may not be suitable. And by saying that, you should not take it in as a limitation, even though it is a limitation, but still 3D printing plays a vital role in realizing a prototype, in realizing some kind of a batch production is possible. And batch production in the sense only tens or 20s of quantities is required. Beyond that, you may need to have some kind of a design change, and there is not any kind of a similarity between the batch what you have already processed and the batch you are right now processing. Under these circumstances, definitely mass production may not be a viable solution. Rather, you can go for 3D printing the objects. And it has, in fact, having a huge cost advantage. And when you look at that, the global market for metallic additive manufacturing for aerospace alone at $1.9 billion in 2016, and it forecast to reach $20 billion, almost 10 times increase is projected by 2024 within a very short time, where other manufacturing systems or competing technologies cannot match this kind of a speed. And compare this situation in India again, almost 10 years before, you don't see a lot of industries are using 3D printing systems. But when you look at in the recent times in major cities, they have installed 3D printing system, and they are serving to commercial markets, more specifically for automobile and aerospace. And I have also seen some of the applications for dental and medical related applications and other cosmetic related applications and consumer products. A lot of things they started 3D printing in the recent times, and slowly the market started flourishing. And once you realize many people started using the system, possibly you can expect a huge price reduction in terms of capital investment, and this becomes one of the important source of doing business. And if anyone wanted to involve in 3D printing based entrepreneurship, and this is a right time or right instance that you are seeing a huge market potential, as the government is trying to promote Make in India and other Atmanirbhar based schemes, where almost lakhs of crores of rupee they wanted to divert to only Indian MSMEs, those who wanted to involve in defense-based production and other related production systems. So this is a right point when the entrepreneurs, when you like to invest in some of the technology, I feel 3D printing is the right technology, where still a lot of interesting and innovative things are happening, and you can be part of that growing market. So coming back to the topic, and here you can see what is the ratio by which majority of the systems, markets or verticals that is using 3D printing. And when you look at that, 31.7% of the vehicle, motor vehicles or automobile, and followed by consumer products, a lot of things are coming in. Then you have machines, medical, academic, aerospace, and other related things. And earlier there is little skepticism that compared to bulk material property or the cast material, whether the 3D printer materials are airworthiness, because whenever you wanted to use that system in a highly reliable, demanding situation like aerospace industry, you need to get a lot of clearance, certification, airworthiness certification, everything. And for your information, a lot of products now got cleared by the certification agencies, and they are promoting this kind of 3D printer systems for the aircraft manufacturing. And GE is one of the leading manufacturer of 3D printed aerospace components, and even they have proved that they are able to produce the entire turbine using 3D printing technology. And later, when we talk about in the application, I will give some insight into that systems. And one of the major target in the case of 3D printing is lowering fuel costs through lightweighting. And most of the cases, we attempt to this particular strategy, lightweighting. So lightweighting is essential in many of the cases. Without losing the structural integrity, you need to have some kind of a system when it is lightweight, but it still performs the functional property. Then possibly you can say that you have saved a lot of material, and you can have reduced the cost. When you talk about you are doing this strategy in automobile, then much of fuel efficiency that can be done. Another important thing why we are going for 3D printing is parts consolidation. So parts consolidation, it's another important strategy. As you know that whenever you have in a kind of a product a number of parts or sub-assemblies are there, then the rate of failure is very high. The reliability will be very, very low. And when you say that, when you are reducing the parts and combining the parts into, when you're combining 4 parts into a single part, that means you are eliminating the chances of failure 4 times into 1 time, right? So ultimately, when you're doing this kind of strategically reducing the number of parts in a product, and you are attempting to do some kind of part consolidation, then possibly you have a better improvement in the reliability of the service. And through 3D printing, it's completely viable, because through a lot of design simulation, modeling technology, you can understand which are the parts that can be combined. When you are combining, whether it is affecting the assembly, when you are doing that, you don't bother about the design for manufacturing, because the design for manufacturing will have always a constraint for the traditional manufacturing, enabling it to manufacture without any issue. But in the case of a 3D printing, whatever be the complexity, whatever be that intricacies involved, possibly it will able to meet those kind of challenges without any issue. So parts consolidation is one of the important strategy that you can look on whenever you think about 3D printing. Then increasing manufacturing productivity through innovative 3D printer casting patterns. So why not we go for a pattern production itself rather than using it a product? Because this is a part of the rapid tooling, rapid manufacturing, where prototyping, where the 3D printing plays a vital role. So beyond that, you can extend the 3D printing capability to rapid tooling also, where you can produce the casting which is required to produce component in a mass production. So direct metal printing of airworthiness spots, that is again another important things. So basically, when you look at any general additive manufacturing textbook or some papers, they made a lot of classifications. They come out with quite an interesting numbers of classification. And today in market, you have thousands of varieties of 3D printer dealing with different technology. But ultimately, all these kind of varieties that can be brought under this any of the three categories, simply speaking. And due to just to give a general audience some information, I don't like to confuse them with talking about more on multiple varieties like continuous fiber based 3D printing and other methods which is emerging in the recent time. Rather, what is the base, how we can classify under these three different categories, like liquid based, powder based, or a solid based. So most of the things, most of the 3D printing technology may fall either of this category ultimately, but some may not fall in that, but the basics of operation may be similar to that one. Under liquid based, we'll talk about stereolithography, jetting system, and digital light processing. Under powder based, we can talk about selective laser sintering, selective laser melting, direct metal deposition, and electron beam melting, which is recently coming up. Under solid based, we have fuse deposition modeling and sheet stacking technologies. So we will look at each thing little in brief, and when you wanted to have an elaborate information, probably you can refer any kind of a standard textbooks, or you can browse through the net where you have a better possibility to understand in deep the process characteristics and other related things. So lithography, basically a kind of a curing technology, right? It is one of the base AIM process. As I said earlier, in 1984, Charles Hull used this process to 3D print some of the models, and stereolithography is the forefather of the 3D printing systems. And here you'll be having some kind of photopolymer. Photopolymer is nothing but liquid thermoset resin, and being said that a thermoset resin, essentially it will become solid when it is being exposed to some kind of a light source, basically the ultraviolet laser light. So when the ultraviolet laser light, when it is passed over that thermoset polymer, the photopolymer, the resin, what happens? It will become solidified. So the intensity of the solidification or the depth of solidification depends upon the power intensity of the ultraviolet laser that is being passed on. So for example, in a basin, you have a kind of photoresin or a photopolymer. And if you are passing a laser in this direction and in a line, this will get solidified. When you pass on a laser in this direction, in a circle, this will solidify. So according to the pattern of the movement of the laser, it will selectively solidify, right? The surrounding material, the surrounding polymer will just hold the solidified material, and then you are pushing down one layer of the photopolymer using some kind of XY table, and then again you are passing the laser strategically. So when you are passing the laser like that continuously over and over again and again, what happens? You are slowly building layer by layer a polymer based a product or a component which is pre-programmed in such a way that the laser is actuated. So when you wanted to produce any kind of product, according to the product shape, the laser movement will get pre-programmed to make a movement so that you can realize that kind of a product finally. So that's what given here in the steps. I don't like to read through that steps, and what is that I have explained here, that will be enough. So finally, some kind of curing process also been done in order to realize that entire solid material. So that's what's shown here. You can see that there is a kind of a chamber in which you are having a liquid photoresist polymer or a resin, and the laser is being passed wherever you wanted to solidify or realize a kind of a solid material. Then you are lowering this particular platform one layer thickness, and then the laser follows the path, and ultimately at the end of the complete system you have one finished product or a prototype. In jetting system, almost the same principle of photopolymer that is being used. Again, here we are going to use a thermoset photopolymer or a resin, and rather than immersing or having a kind of a resin bath or a resin chamber, here, as we have seen in inkjet printer, it is being put in a drop by drop. So that is the only difference, right? So drop by drop, wherever you require the pot, then you put it in the form of a droplet, and immediately the droplet will get cured by the UV laser curing light, and then the platform moved again to one position. And here there is a possibility also to have two different heads, one head for the primary material supply and another head for the supporting material. So likewise, when you are trying to build layer by layer, and the droplets can be falling wherever you wanted to realize the solid material. So here the print head is positioned above the build platform, and the droplets of material are deposited from the printing head onto the surface where required, using either thermal or piezoelectric method. So thermal, the system where you little melt the particular polymer material, and then it becomes liquefied and then falls as a droplet. So the droplets of material solidify using ultraviolet light and make up the first layer. So further layers are built up as before on top of previous. Post-processing will do removal of support material. So likewise, you can build the system. So here you can see that the droplets are falling on the material wherever it's required, and parallelly the supporting material also falling, and you have a laser system here to cure, and then finally you can realize this particular product. And binder jetting, this is another form of jetting system, and rather than having some kind of curing system, here there is no such systems are involved. Rather, you have a kind of liquid binder to bind the powder together, right? It's more of a kind of process where you apply a powder, then you apply a binder in the form of ink jetting, and wherever you wanted to collate the powder together, and after each layer is printed, again the powder is recoated over the material, and the process repeats. Finally, you realize a 3D printed object over that. So here you can see that steps. Powder is deposited, inkjet applies, and here wherever you wanted to collect the powder, consolidate the powder, then you can have that powder here, and again you can recoat. So likewise, you repeat the powder deposition. Finally, you can see that a kind of a solid object got generated. So it is called binder jetting, and so you don't need any kind of curing system here, rather than the liquid binder bound the powder together. So you can see the process. It's depositing powder wherever it's required, and then the binder is applied, and the table moves one step downwards in order to build the entire workpiece or a component what you intend to build. And the digital light processing, it's little innovative process, and one of the fastest process in the 3D printing arena, where you can realize the product at a very faster rate, as the curing rate also extremely high. And in most of the situation, you pass on the curing media or a laser light or a binder from the top. It is completely from the bottom. So you started building from the bottom, and you have normally a resin tank here, and there is a kind of digital micro mirror device. So this is a very critical system in this digital light processing, a digital micro mirror, and it's a component made of thousands of micro mirrors used for navigating the light being projected by the digital light projector. So you have a light source, and this is in fact a light that is being used to cue the system, and it falls on the digital micro mirrors. Then it get focused, and then it goes to the tank area, where the bottom of the tank area is transparent. It falls according to the curing strategy, what you wanted to cure and what you don't like to cure. And from the build platform in the Z axis, it will get attached to the surface. Then slowly, when you are moving in the top upper direction, then possibly you can build any component you wanted to build according to the light reflections you already planned. So this is one of the fastest processes, as I said earlier, and you can realize any kind of a complex shapes using this digital light processing system. And coming to powder-based additive manufacturing processes, in earlier case, liquid-based, the starting material, we call it as a starting material. The starting material is in the form of liquid. So from the liquid, you are using some kind of a strategy to cure the liquid into a solid form. But here in the case of a powder-based AM processes, the starting material preferably in the form of a powder, right? So powder, either it can be a composite powder or a polymer powder or a metal powder when you are talking about metal-based 3D processes. So there is a little difference between this selective laser sintering and selective laser melting. So most of the metal additive manufacturing system, they fall under the category of SLM. SLM is a selective laser melting. So you need to melt the metal powder in order to fuse together to form a layer, a solid layer, and finally a product. And if you wanted to do some kind of pre-bound polymer or a ceramic or a glass particle, and if you wanted to just fuse the material using the laser energy, then it is more of a selective laser sintering. You are not raising the temperature to the melting point of the material, rather you are just sintering that one. So sintering finally will get fused, and just for realizing the prototype, you don't need a kind of a complete melting or solidification, something like that. So in the case of SLS, tiny particles of plastic, ceramic, or glass are fused together by heat from a high power laser to form a solid three-dimensional object. So here, it not necessarily to be a metal, it can be a plastic or a ceramic or glass. And metal additive manufacturing may not use SLS because it may be very difficult to fuse together a semi-molten material. Rather, you need to have a complete melting of the material powder in order to fuse together. And after doing that, a roller will apply a layer of powder. Then the laser will sinter the powder according to the 3D file, and the build platform will lower before applying a new layer of powder. So basically, again, it is a layer by layer deposition of the powder particle. Sintering happens, lower the powder bed by one layer thickness, then again apply the powder, lower the layer by one layer thickness, likewise it goes. So here you can see that the selective sintering process, they are applying one layer of material, and the laser that is sintering selectively where you wanted to realize some kind of a solid, then again it is falling on that one, and the process repeats until you build the entire component. And the selective laser melting, it's a more straightforward process. You completely melt the metal powder that is lying on the bed wherever you wanted to realize the product, and then you lower the bed again and repeat the process to finally realize the entire component. That is more of a selective laser melting. And there is a lot of other names also being used: direct metal laser melting, or laser powder bed fusion technology, or simply powder bed fusion technology. And commercially, a lot of 3D metal printers, specifically on PBF, that is powder bed fusion technology, is available. And this is one of the rugged process where you can realize the component without much of the component distortion, even though the process is very slow. And you can look at that here in this case. Nowadays, they have the system that can accommodate any powder when it meets the specification constraints of the OEM, and you have the liberty. Earlier, it is not the case. You need to purchase the powder from the OEM, and that ultimately affect the end product cost. But nowadays, you can procure the powder from anywhere. Only thing is you need to look at the powder particle size, powder shape, and if you sieve that powder using the siever provided by the manufacturer, then confidently you can use the system for producing any kind of a metal-based product. And here, the thin layer of fine metal powder are evenly distributed using a coating mechanism onto the substrate plate that is fastened to an indexing table that moves in the vertical axis. So again, layer by layer deposition, move the powder bed down one by one the layer. Then finally you can realize the entire, product. So once each layer has been distributed, each 2D slice of the pot geometry is fused by selectively melting the powder using layer. Basically, this 3D printing systems are uh, 2D area only it will cover in X and Y direction. And since you are lowering one by one and fusing the powder in the Z direction, finally you can realize the entire component in a 3-dimensional pattern. And direct metal deposition, it is more of laser cladding, right? And if you have a coaxial powder feeding nozzle like this, whether it is a lateral or off-axis system or a continuous coaxial system, where you have some kind of a powder feeding mechanism where the powder is fed into the coaxial nozzle of the laser, and the laser light will come from the middle, and then it melts the material which is meeting the already prepared layer, and then it will get deposited. So likewise, if you mount the entire coaxial nozzle like this in a robo arm or a kind of XY gantry, and if you move that entire system in a pre-programmed manner, then finally you end up in producing the entire product. Even some of the industries, they proved they can build the entire turbine blade using this direct metal deposition based technology. So here heat is generated using a focused laser beam that is sufficient to melt the surface of the substrate to form a small melt pool, and the material is added to the melt pool using focused powder stream or a wire feed. Here rather than using a powder, you can use a wire feeding system also, and you can manipulate the substrate like that. Here you can see that you build a kind of cylindrical material one by one, layer by layer, and you can realize the final product. So likewise, you form one layer over other like this continuously, and you can build the entire material for the system. And electron beam melting, almost the process execution strategy is similar to laser-based powder bed fusion technology, except that rather than using laser for melting the powder, they are using electron beam to melt the powder. So only advantage what they expect from electron beam based systems are the distortion levels are very, very low because electron beam it is not a very high intense heating system, and here electromagnetic radiation in the case of a laser that has a huge heat content that will try to distort in certain situation. Normally, if you print using laser based systems, that will lead to some kind of tensile residual stresses inside that one. You need some kind of stress relieving strategy before using it for a final product, except that all other processes are similar. And the electron beam system, in fact, do have a lot of difficulties in terms of beam manipulation. So when you wanted to deflect the beam, you need to have some kind of magnetic deflection coil. But with the laser being an electromagnetic radiation, you can simply move the beam by moving the mechanical system. And another limitation of this electron beam system is the limited in terms of the size of the part, because the entire process need to be done in a vacuum, because the heating happens by the kinetic energy of the electrons that is hitting the material, and then it is converted into a form of a heat that would be used for melting. And if you are using it in an open atmosphere, then you have a lot of chances of getting the electrons distracted with atmospheric molecules. So being this kind of a disadvantage is still existing, but still due to the advantages of low distortion, the electron beam based systems are nowadays also picking up in the market. So here you can see that the powder feeding chamber, and you have an electron gun here, triode, and which is melting wherever you wanted to realize the solid part. And then there is a recoater which is removing the excess deposited material, and then the electron beam is used to melt the material, and finally you can realize the finished product. So some of the comparison between electron beam and laser based 3D printing technology, and most of the things are self-explanatory, and probably in any of the textbooks when you look at you can able to see that this kind of the comparison. Coming to this solid based, in an earlier case we use liquid as a starting material. Then in a laser based system, predominantly we used either a powder or a wire. And here in a solid based, it's they'll be using purely a wire as a starting material, a kind of a filament coil, and this fused deposition modeling. Even we have one FDM printer. This FDM, it's a widely accepted process, and where you have the material in the form of a wire, and the wire is fed through the a kind of extrusion head, and in the extrusion head you have a kind of a heating coil, and the coil will heat up the material, and then it will deposit wherever you wanted to deposit. So mostly this the curing head or extrusion head will be moving in a XY direction, and the platform will move down in the Z direction. Here you can see that there are two different colors. One is the dark blue, another one is light blue. And the dark blue, that is the part. And the light blue, that is the part support. So both the things that you can simultaneously feed using the, the extrusion head. And at a time, it can deposit only one, depending upon the part geometry. When you have complicated part geometry, here you can see that there is a overhanging structure that is extending up to that. So if you don't have this kind of supporting material here, you cannot build this particular portion. Likewise, here inside you have a lot of support that is required. So accordingly, first you need to print this supporting part and then you print the main part. So likewise, you have a separate feed spool to feed build material as well as the support material. So finally, you end up in generating any kind of a part using this particular technology. It's a fused deposition because you are melting and fusing. So that the name fused deposition modeling. You can see that there is a wire feeding spool, and mostly these are all thermoplastic material, and those thermoplastic material that is being fed into the system, and using the heated head, it will melt and fuse layer by layer, and then the platform is being lowered one layer to realize the final product. Laminated object manufacturing, it is again a kind of a the technology where they use a solid-based material, and starting material preferably in the form of a sheet. And you need two components. One is sheet, another one is binder. And a laser beam is used to cure the binding material as well as to cut the excess material. And there is a heated roller that is being used to fuse the material together, almost similar to our certificate lamination process, where you put a paper and above that one bottom and one top layer of polymer material that is heated up and then it is fused together. So here the sheet is adhering to the substrate with a heated roller, and the laser traces the desired dimensions of the prototype, and the laser cross hatches non-part area to facilitate waste removal. So this is the part area, and the rest of the area is non-part area. So you can cross hatch so that it can be removed easily. Again, the roller makes one movement, and then the heated roller also rolls over the surface. Likewise, the process repeats to realize the final product. So that is about the laminated object manufacturing. So this is a very brief information about the classification of the additive manufacturing system. Either it's a liquid based or a powder based or a solid based. And we look at some of the applications of in different verticals. Aerospace, where some of the components are very unique. Some of the components need a lot of improvement in terms of reliability, and you don't need some components in bulk, some products in bulk, and some of the parts where you can better improve the performance. So under these cases, the aerospace industry's demand for additive manufacturing systems are ever rising. And this is one particular example where it is a fuel nozzle, and the GE's new LEAP passenger jet engine uses this kind of a fuel nozzle. And look at the enormous improvement. This is 5 times more durable compared to the conventionally manufactured fuel nozzle. So it is 5 times more improvement. So what is the simple strategy that they have used here in the case is they use the strategy called part consolidation. Earlier, they have number of parts in the fuel nozzle that leads to failure, and now they use the strategy part consolidation and 5 times improvement that they have achieved. And some 3D printed part and the combustor portion of the nickel alloy. You can look at the complex shapes, what is being there. And here there is a kind of a titanium aerospace bracket, and with a suitable modeling analysis and structural simulation, they have put some kind of lattice arrangements between the part, and without reducing the structural integrity, they have reduced the weight up to 63%, which is enormous. In an aerospace, even a 1% weight reduction, and if you are saving a fuel, it has a lot of importance. And a 63% weight reduction, that is unimaginable in any of the cases. And here you can see that Syntavia, a company called which is manufacturing 3D printed turbine blades. And mostly you look at here, the turbine blades are having cooling holes running throughout the blade in order to keep the blade in a with a controlled temperature. Otherwise, the thermal deformation, thermal disturbances, and the decomposition of the material will happen. So in order to avoid all those things, they try to create the cooling holes once they manufacture. And even we involved in some of the projects where we need to machine very minute cooling holes, right, that is running into few hundred microns. And laser is one important source by which they can do. And this electrical discharge based machining, drilling that you can do. But still, those are the processes is very slow. For example, when you wanted to drill such a number of cooling holes, you may be spending hours and hours of time. Rather, if you print those holes, while doing that printing itself, then it becomes an integral part of the system. So the printed turbine blades with the cooling holes, it is highly demanding in the turbine industry, as you don't need any separate post-processing to create the holes. And this is one prototype of GE, where they have printed the entire turbine blade, a working assembly itself. And they proved that it is possible to print that entire turbine blade with a complete integration of all the different stages of the turbines, and it's ready for use, a kind of a system which is very futuristic, and such a kind of a system is highly demanding in the industries in the recent times. And in medical, you have a lot of interesting applications are coming in. One of the major applications are printing implant. And implant printing is very, very demanding in the medical industry, as most of the requirement for implants are unique. No two human being has the same kind of bone structure, or even though the skeletal topography or the dimensions will be same, but there will be a lot of difference in terms of the appearance, in terms of the kind of a system available with every human being. So when you wanted to prepare a kind of an implant, just a kind of a rod, when you wanted to treat an orthopedic kind of an injury, then no problem. But a hip replacement or a dental implant that need to be produced uniquely to the patient. So such a circumstances, you use a kind of a scanning system to exactly map the dimensions of the particular patient. Then that can be imported into a kind of a 3D model, and that finally can be realized in the form of a 3D printed product. So here you can see some kind of orthopedic implants and dental implants, and the 3D printed cortex cast. Earlier, when you look at that, we may be using a plaster of Paris whenever you wanted to heal a broken bone. But nowadays, without losing the strength, but it has a lot of aesthetic look, you can prepare this kind of cortex in order to cure broken bones, and a jaw implant, and the ribs of the bone, or even a kind of prosthetic implants, very, very lightweight. Here you can see it's a kind of network structure, simply connecting with the wires or something, but it has a huge strength. So transportation, you have a lot of interesting application. Here it is an electric shuttle OLE. It's completely 3D printed. Entire the material what is being used in this, it's a kind of a demonstration of a e-vehicle that is printed completely. And this is another demonstration of a mass production, a batch production, where you can produce number of systems, a complicated, it has a complicated curves, flanges, everything together you can print. Even you can print an engine block or a front panel or this chassis end or even an entire chassis of a bike, something like that you can innovatively think about. And a lot of innovative consumer products are coming out from the market. You can look at this kind of door handles with a lot of lattice structure, a hole which looks beautiful, and the ear headphones and a chair with this kind of a structure. Imagine that producing the same with what do you say, conventional systems, creating, you need to machine out completely this structure, which is not required in the case of a 3D printed system. And here you can see that a 3D printed spanner, a completely working model, right? It's a completely working thing. And a trimmer, a watch, and a helmet, multicolored helmet, where polyjet 3D printers can do that one. And depending upon the size of your head, you can print the helmet, because sometimes we are sacrificing the sizes, then we are getting some closely matching sizes and doing with that. But with the 3D printed, you can exactly print what your head size is. Similarly, 3D printed shoes, you can exactly print what is your foot size. Because when you go to the chapel shop or a food shop, you have a numbers with the 6, 7, 8. If your foot dimension is 6.5, you need to go for 7 only, right? So if it is 7.1, you need to go either with the 7 or 8. So you need to have some kind of a sacrifice here. Rather, exactly to match your requirement, you can print the shoe. And 3D printed cloths, that is again coming up according to your needs, that you can do that one. So what are the systems available at NIT Trichy? There are more number of systems already have with the different departments. Just what is that available in our manufacturing COE and Center of Advanced Manufacturing that I am showing, which is very important, that we are doing a lot of work in these printers. And we have one, already we talked about that fused deposition modeling based 3D printer system. And this Stratasys F270, one 3D printer, what we have it in our lab. And you can have a 1 cubic feet printing using this system, and multiple materials like ABS, ASA, and PLA that you can use with the different layer thicknesses, as well as 100 and 127 micrometer to 330 micrometer that you can produce. And the accuracy of part production is plus or minus 200 microns. And these are some of the 3D printed parts that we have done using our FDM printer. And we have 1 year before installed one 3D metal printer supplied by Ampro. And it has a huge build volume of 500 by 250 by 250. And the powder layer thickness that can vary between 20 micron to 100 micron. And a very good accuracy of 50 micron. And the printing rate is 5 centimeter cube per hour to 50 centimeter cube. And actually it's a twin laser system. Why we gone for a twin laser system is the productivity can be entirely doubled. For example, when you look at here, that this is the build platform, and this is 500 mm, and this 500 mm is being divided into 2 portions, and one laser will cover this portion and another laser will cover this portion. And if you have a big part that is covering the entire build area, and both the lasers will simultaneously operate, and that will print the entire part. And if you have a number of parts, small parts, some parts that you can locate here, some parts that you can locate here, so that you can simultaneously print in order to save the time of printing, because most of the time the printing speeds are preferably very slow, and you need to use this kind of a strategy in order to improve the printing capability. And basically, the movement of the laser beam is controlled by galvo scanning. and you can go up to 7 meters per second. It's fixed actually. It's a fiber laser system, twin laser. And multiple materials are possible with our printer. And aluminum alloy, we have aluminum silicon, 10 magnesium. Steel, we have 316L and 15.5 pH. Titanium, the titanium grade 5, it's a medical grade actually. Titanium 6, aluminum 4, vanadium, and we have a pure titanium also. And under the Inconel alloy, we have Inconel 718 and Inconel 625. And this multi-material that is possible right now. And we can go with any kind of a material, but only thing is we need to get a parameter from the OEM, because developing the parameter by ourselves, it's too complicated. We don't know in a particular layer thickness, what is the kind of melting that the laser is doing, how it is hatching the entire pattern, and how it is using the power to reach the contours. All those things need a lot of critical understanding. So we normally depend on the OEMs to supply the parameter. So we have right now the parameter for all these materials, and basically we started using this particular printer for printing that SS316L stainless steel. And tomorrow morning, I think we have a demo section. In that, we try to cover lively this metal 3D printer, as well as, if possible, the fused deposition modeling 3D printer by tomorrow morning. And let us see how effectively that the time is being used. And these are some of the metal printing what we have done in the recent time, and just a simple solid blocks that we have printed earlier. And here we printed the same block with the 45-degree inclination and without any support structure. You can see that here we don't use any kind of a support structure, and up to 45 degree you don't need a support structure. The powder itself will be supporting that one, and when the angle is more, then definitely you need a support structure. And some simple cylinders that we have printed. And this is one part you can look at here. We have printed this lattice structure. This lattice structure, this is quite interesting to look at, and try to imagine if you wanted to do the same with conventional manufacturing process, very, very complicated to produce this kind of a lattice structure. A lot of intricate machining is required, and sometimes it may not be feasible to produce such a kind of a lattice structure itself. So the regional additive manufacturing market, when you look at in North America, it's pushing to increase from $2.35 billion to $7.65 in 10 years time period in 2025. In Europe, it is 1.8 to 7. In Asia Pacific, it's 1 to 5.6, and rest of the world 0.1 to 1.1. You can see that what is the enormous projection that the 3D printing market that is going to evolve in the near future. And there are a lot of key challenges that we are facing, and getting a right product that is very much interesting in the case of a 3D printing system. So printing a part with the right shape, because little distortion will be there, and what is the kind of an allowance that you need to give in order to get the exact shape, and what is the kind of a post-processing requirement, that all big question. And ensuring part qualification, as I said earlier, distortion, shrinkage, porosity, delamination of layer, surface finish. Normally it is poor here, because you are converting the powders into a molten material, and during molten pool solidification, some kind of ripples will form. Even when you look at here very closely, you have some kind of rough surfaces only. So definitely it needs a kind of post-processing, a kind of a machining is required. So how to overcome that one, that's very critical. So which raw materials and machines for which results? Is it really worth it? That's $1 million question, but really it's worth it, because the rapid prototyping is one of the inevitable source, and Industry 4.0, again, it's an inevitable source. Some of the complicated, intricate shops, inevitable source, but normal manufacturing, definitely going for a 3D printing, it's not a wise decision. Our operators being put at risk, obviously, when you're dealing with metal powders, you need to be very careful because when you're inhaling the metal powders, because it's floating on the atmosphere, you need to have a proper apparatus when you're within that 3D printing area. Tracking parts to ensure regulatory compliance. Normally, in a mass production, you'll be making some kind of numbers, which batch correspond to which machine, at what time period that the machining happened, so that you can trace back if there is any kind of deviation from the planned process. So those kind of systems, whether that can be implemented in the case of a 3D printer. And the part size and material limitation, obviously it is there. And when you wanted to print a very bigger part, you need to have a huge printers, and that it's a lot of capital investments is required. So finally, I will just touch upon what is the role of additive manufacturing in Industry 4.0. And Industry 4.0, you might be knowing that it is fourth industrial revolution. Right now we are talking about starting from 2010. The Germans have come out with a kind of industrial revolution or industrial practice or smart manufacturing, and which is driving all the industries to think beyond automation. That is what the Industry 4.0 is talking about. Now the question is, what is the problem with the current system? What is the improvement that we need to put on in order to match with the current requirement? And there is no problem with the current system, as we are 100% fully automated systems are available in practice. But beyond that, the present changing market is requiring. And these are some of the enabling points which is driving the requirement beyond Industry 4.0. So enable rapid manufacturing of new products. Because of the changing markets, you need to produce lot of new products that need to enter into the market. So you need to be quickly realign your entire system. Rather than being a rigid manufacturing system, you need to have a kind of a complete realigned system. And the dynamic response to product demand. The product demand is completely need to be tracked very closely. So whenever there is a dynamic response comes, how you are going to meet that dynamic response, that's very important. Then real-time optimization of manufacturing and supply chain networks. Again, this is one of the important Industry 4.0 driving factor. So here, when you look at that, in the first industrial revolution, we talk about mechanization, water power, steam power. Roughly in the late 18th century to the early 19th century, this particular practice was there. And slowly we moved from the first industrial revolution to second industrial revolution, where mass production, assembly line, electricity that drives the entire operation. This is early part of 20th century. But in the mid of 21st century, there is a lot of usage of computer programs and automation. What I can say, the use of robotics, the use of PLCs that revolutionized the entire way we do manufacturing. And that is more about third industrial revolution. Somebody always confused between automation and Industry 4.0. And Industry 4.0 is not about automation. Automation already we have done in Industry 3.0. We have done enough of automation. 100% automated systems are available. But in Industry 4.0, beyond automation, we are talking about smart manufacturing. The machines will think by itself using the artificial intelligence technology and take decisions by its own in a decentralized manner. And the entire digital factory that will be running in a different platform, and all the permutation combinations will be done before taking any kind of a decision. So the fourth industrial revolution, what they are primarily talking about is a CPS, that is cyber physical system. So there is a merge of the cyber and the physical system. The physical objects are our machines, the sensors and other systems. And the cyber systems are the connectivity, how we are connecting and how we are storing the material, how we are data, and how we are analyzing the data to realize a kind of advanced manufacturing, that is the smart factory. So machines are augmented with wireless connectivity and sensors connected to a system that can visualize the entire production line and make decision on its own. So this is very, very important and critical point. So that the decisions are taken by its own, not depends on any human intervention or input. So that is the way we look at the smart factory, where automatically decisions will be taken based on the data that is being manipulated with artificial intelligence programs. So this Industry 4.0 that is characterized by 4 foundational technologies are placed along the value chain. One is the connectivity, data, and computational power. So once we realize 5G, all industries, they try to move to Industry 4.0. And this Internet of Things, it is nothing but a skeletal through which we are building our smart factory. And this Industry 4.0, again, that can be called as Industrial Internet of Things, IIoT. So you need a cloud technology to store the data and a blockchain to send the data in a more confidential manner. Then you have an analytical part, that is the second pillar, advanced analytics, data analytics, that is gaining a lot of momentum in the recent time, and how to pick up a lot of trends and information from the data what you have got. And the machine learning, artificial intelligence, all these things are getting in. And the human machine interaction, you have VR, AR applications quite extensively. Robotics and automation, you have cobots, AGVs, and other chatbots. And finally, you have advanced engineering. So in the advanced engineering, you can look at that this additive manufacturing is becoming a part of Industry 4.0. So that I am again telling, in the near future, when all the industries switching over from Industry 3.0 to 4.0, you realize the usage of the 3D printing technology in a more extended manner. Then you talk about renewable energy usage, no more the fossil fuels that they will be using, most of the renewable energy, and something about nanoparticles. So with that short time available, thanks for the opportunity given by the organizers for giving a talk on this particular topic, some introduction to additive manufacturing and how it connects well with the the Industry 4.0 related concepts. And if you have any questions, I am very glad to answer. And this InventGlow, that is a startup of mine. That is the spin-off company from this manufacturing COE, where we have a lot of digital manufacturing solutions and the 3D printing systems. And we are addressing the industrial need through these startups rather than addressing through the industries, through our institute sometimes. And yeah, thank you very much. And if there is any question, I'm very glad to answer that.
Thank you, sir. Thank you for such a wonderful session. Yeah, we would like to take a few queries or questions if anyone is having. Participants, you can unmute and you can ask. Any questions? Or you can write on the chat box.
Yes.
Excuse me, sir.
Yeah, please.
Good morning. This is Rahul. Sir, you told that up to 45-degree inclination, we can print that up to 45-degree inclination. Sir, what is the optimum thickness so that we can print a smooth surface? Because if we will increase the layer thickness, thickness of the layer, then obviously it is not going to print very smoothly. So what will be the optimum thickness?
So there is no relation what you can say this is optimum thickness, this is not optimum thickness. And here the layering start from 30 micron to 100 micron, that is possible. And obviously when you are going with a very high layer thickness, you are losing the surface finish or a quality. So bigger layer thickness always correlated with a higher surface softness. So that is one point. Second thing is as I said earlier, we cannot say this is optimum or this is not optimum. For example, your prototype, it is just for to look at how the shape is. Under these circumstances, you don't need to go with a very, very low thickness just to increase the speed of the thing. For example, if you have a 1 mm height, and if you are going with a 40 micron layer thickness, you need to lay 25 layers, right? So if you have a 1 mm thickness and if you are going with a 100 micron thickness layer, then with the 10 layers itself, you can realize the pot. So that your time of printing will come down if you wanted to sacrifice the surface quality. And if you wanted to print something with a very high quality, definitely you need to go with a very, very low thicknesses. So always there is a kind of a trade-off between the roughness and the part thickness, and what is the kind of your end result or end product, accordingly you can design.
And sir, what about the strain?
Strength part, there may not be much difference, but you need to make some kind of an analysis how the strength varies whenever you are varying the part thicknesses. For example, even in our system, metal printing, when you are using a 40 micrometer thickness part, you have a set of laser process parameter. And if you are going with a 30 micrometer, we have two different parameter combination right now. And if you are going with a 30 micrometer for the same material, completely we are having a different set of parameter, right? So what I mean to say is, when I am going with a 100 micrometer parameter, ultimately the OEM will try to increase the laser power in order to melt the higher thickness of layer that you are depositing every time. So under these circumstances, they try to create a kind of a uniform isotropic property across the thickness, otherwise your part will fail. So to my understanding, there may not be any much difference in the strength when you are varying the layer thickness, but you need to work on it. Even in the picture what I have shown with the 45 degree, with the flat and 90 degree, one of the students wanted to understand when the print orientation is changing, is there any kind of difference in the mechanical property?
And sir, what should be the property of the powder?
Powder property, it will match with
That
the
means size.
yeah, size. Here in our printer, the recommended size is 15 to 43 micrometer, a spherical shape powder. And obviously, if you follow that, your part quality will be as expected. When you are changing the powder sizes, sometimes your printer may not accept that one, because the recoater nozzle will be very, very smaller, and you may get clogged with that nozzle. And the powder laser parameter is designed to accommodate that variation in powder sizes. And if you are changing the powder, then you may get some problem in the finished product finally.
Thank you, sir.
Welcome.
Okay, thank you, Rahul. Thank you, sir. Any more questions from the participants? Okay, Mohanty sir, are you there?
Yes, sir. Yes, sir. Yes, sir. Can you hear me, sir?
Yeah, I'm here.
Yes, sir.
Yes, sir. Yes. Good afternoon. Good morning, sir.
Good morning, Professor Mohanty.
Sir, this is Dr. Mohanty, sir. Sir,
Yeah.
thank you very much for your wonderful sessions.
Thank you, sir. Thank you.
Yes, sir. Definitely, our participants learned many things from your presentation, sir. So I hope we will meet once this pandemic is over. You can come to our institute. We can go interaction.
I am very glad to meet you all in person if some chance.
Yes, sir. Definitely will.
Yeah, Arunachal
call you,
Pradesh.
sir.
Maybe I'm looking for that opportunity.
Okay, sir. Okay. Thank you very much, sir.
Thank you, sir. Thank you.
Okay, thank you, sir. Thank you once
Yeah,
again,
thank you.
Andurai Silvan sir, for such a wonderful session. You have one more session lined up tomorrow at the same time. We hope to look forward to that. So with this, we come to the end of the first session of this entrepreneurship development program. I request all the participants to kindly join us back again for the second session, which is starting from 2:30. That will be taken by the Tool Room and Training Center in Guwahati. So thank you once again. Do join us back at 2:30 for the second session. Thank you all.
Thank you, Dr. Subhajit, and all the participants for learning to the lecture. We'll meet again soon. Thank you very much.
Yes, sir. Thank you, sir. Thank you.
Thank you. Bye-bye.
Okay.